my name is Cameron Camp.
I'm Joshua Pickens.
And I'm Tyler Washington.
And we are
Rubik's Revenge.
We call ourselves Rubik's Revenge because a Rubik's Cube is an engineer's dream. A Rubik's Cube is made up of different complex algorithms that help teach perseverance, problem solving, and patience. I'm Cameron Camp, and I am a junior attending University High School Academy. I participate in track and varsity cheerleading.
I'm a senior attending Southfield High School. I plan on going to Clover Stockton in the fall. I participate in football and track, and I'm a member of the Capital League.
I'm Tyler Washington. I attend Southfield High School. I am in a multitude of clubs, societies, and I play a lot of sports, and I'm number one in my class with a cumulative GPA of 4.01.
A bridge is a structure built to span physical objects. They were first used in ancient times when modern civilization started rising in Mesopotamia.
A cantilever is a long projecting beam or girder fixed at one end. Cantilevers are most commonly found in bridges, balconies, and even in some desks. Cantilevers in bridge form are usually used with one on the right, one on the left, and they are both used to support a central span.
Engineers in the 19th century discovered that a bridge which continued along many supports could distribute the loads. This resulted in lower stress on the suspended span and truss, which meant that longer roadways could be built.
Originally, we chose to use the gable design because it was very strong for a truss. However, after testing a multitude of bridges, we realized that it wasn't about how strong the truss was, but it was more about how strong the cantilevers are that hold the truss.
After testing the first bridge, we noticed that our theory was completely wrong. While testing the first bridge, the bridge bent so much that the block wasn't even on the suspended span anymore.
This is our original bridge design. This bridge was 7.9 grams and it only held 2.5 pounds. Initially, when we saw the efficiency, it was kind of discouraging because we put so much time and effort into it, but we had to persevere. This is the testing of that bridge, and this is the moment where we had our all moment and our realization about the cantilevers, because when it broke, we were confused because the truss didn't break and the top cantilevers didn't break, but the bottom ones did. And it was at that moment that we realized that we needed to strengthen the bottom cantilevers and put the majority of our mass into the bottom cantilevers. So these are just a whole bunch of different types of trusses that we could have used, and we had the option of using them. In the end, we decided to go from a gable to a modified flat design. Originally, we thought we were going to use the whole flat design, but after we realized that the top crossing braces weren't doing much to help us, we decided to take them out altogether. We also made another modification. We decided to do a half-through. A half-through bridge is similar to a through bridge. A cantilever through truss usually is supposed to have four sides, a right, a left, a top, and a bottom, which makes sense because the traffic is supposed to go through. However, in a half-through, the traffic still goes through, but it only goes half through. This is test bridge number 6. In this bridge, you can see how we made our modification to our new half-through. And so it only goes from here to here instead of going from here to here and then going across. And the bridge on the end, we decided to keep that one because it kept the top two cantilevers from bowing in when all the weight was put on it. And this is us testing that bridge that you just saw. When we tested the bridge this time, we made another realization that if enough weight was put on the bridge, because we had such long pieces, they would bend so much that the cantilevers would go from being vertical to being horizontal. So they were almost at exactly 180 degrees, and it was crazy. And once we saw this, we realized that we needed to have another brace right here just to give us a little bit more weight that we could hold, and that would raise our efficiency just enough so we could win. And this is our final test. This is actually a video. So, I don't know. We thought this was the final test, but it didn't end up being the final test because we got excited and we did another one. This is test bridge number 7. This is the bridge right before our final bridge. You can see in this bridge that it's significantly smaller than all the other bridges we used. After we made our last bridge, we realized that if all the weight was going to be on the cantilevers, we might as well make the cantilevers as small as possible. So we decided to only make them an inch. That way we had room to get our hands in there so we could put in the cross members and everything else. But we still had to have it so that the cantilever was 2 times the height of the suspended span. So our suspended span ended up being 1/2 inch. This is our final bridge. This is our final bridge before the final bridge. We made this one, and it's a replica of the final bridge so we can test it. In this bridge, the only difference between the last one and this one, and I don't know if you can see it, but we made a 3rd cross member, and you can actually see it in this bridge, not that one, or broken bridge. We just tested it, it didn't go well. You can see the 3rd cross member that we put in, so when it turns to a 180 degrees, it actually squeezes it on this one, and we get just a little bit more mass. Okay.
After our initial failures, we had to take some time and regroup. We needed a design that was as light as possible, but could also hold a lot of weight. The less material we used, the more bend that we had. And we needed bend more than anything to hold a lot of weight with such long pieces that we had.
This is the page for our calculations. We used sine, cosine, tangent, and Pythagorean theorem to get the angles for all of the triangles that we ended up using since we had so many small triangles in such a small space. We also used the efficiency equation, which was 454 times the mass that the bridge held divided by the weight of the bridge itself. And then that gave us our total efficiency. So we could see if we were doing better or doing worse in our bridges.
In the beginning, we did not believe that this competition in school had nothing to do with each other, but we were completely wrong.
There are many different jobs in the bridge constructing field. These include civil engineering, repairman, maintenance, overseers or supervisors, construction workers, transportation, bridge engineers, structural engineers, bridge electricians, heavy equipment operators, transportation engineers, environmental engineers, geodetic engineers, and steel workers.
So restoration of cantilever bridge can make the bridge so it holds up to 20 tons. When you're making an adjustment to a bridge and you're restoring it and it has a new limit for it, it's always important that you make a sign very far away from where the bridge is, very far in advance, so people can know, hey, I think my truck is too large, maybe I shouldn't cross this bridge, save a life.
Thank you, and that concludes our presentation.